Sandoval Olascoaga is Assistant Professor of Human-Computer Interaction and Inclusive Design at the School of Architecture and at the Khoury College of Computer Sciences, both at Northeastern University. His work combines design, computing, urban data, and public service to provide formal computational design methods that allow the broadest set of community members to shape their own environments sustainably and holistically with the support of computational intelligence. The Scalable Design Participation Lab, which he directs, develops information models for design collaboration, computational interfaces for accessible multi-user design, algorithms for large-scale design synthesis, and machine learning models for civic data collection. I had the pleasure of meeting Carlos at the Encoding Experience event in Boston earlier this year, and I'm excited for his talk, drawing together computing and community participation in the design of the built environment. So please take it away, Carlos.
Awesome. Thank you so much, Jackie. And thanks, G and Prue, for inviting me out here today. Let me figure out how to share my screen. Okay, cool. I think that worked out.
Yeah,
okay.
we can see your screen.
Cool. Perfect. Awesome. Hi, everyone. Thank you all for being here with me today. I know some of you may be out west, and it might be a little bit early, so thanks so much for hanging out. As Jackie mentioned, my name is Carlos Sandoval Olascoaga, and I'm an assistant professor at Northeastern University, where I run the Scalable Design Participation Lab. We are a group of computer scientists, planners, and designers working on leveraging computing to center community participation in the design of the built environment in ways that are accessible, contextual, and scalable. This is Mexico City, where I grew up. My current work and research interests have been largely shaped by my experiences growing up in Mexico City, which, as many of you may know, it's one of the largest cities in the world. Over the past few decades, Mexico City has grown exponentially and has been shaped mostly informally by its residents. This has made me aware of the pressing need to be able to connect designers with the communities that they serve in a scalable manner. In Mexico City, just like in many other places around Latin America and the world, lower income residents have been migrating into the city, mostly to the outskirts of the city, oftentimes building their own spaces in ways that are structurally unsafe or that don't have access to public services like water and sanitation, and without following an urban development framework. But Mexico City is not unique. In fact, in the next several decades, we are projected to build more urban fabric than we have in the entire human history, which is kind of insane, building the same amount of buildings or cities that we currently have. And most of this development is going to continue to happen informally without the help of architects, designers, and planners. It's already happening in China and Africa and other places. So the work of the lab and my personal research engages with these issues through two main interrelated goals. We first develop computational design approaches and tools that are accessible and inclusive to the participation of the broadest set of designers and community members. And second, we aim to allow community members and planners and stakeholders to collectively design the built environment at scale with the support of computational intelligence. But these goals are approached first and foremost through a critical understanding of the computational history of design tools and planning tools. I like to think about the past and how this past of computational tools have shaped the ways in which we can use them nowadays. And I like to think about this past to get inspired about the future potentials of design and planning tools. And more importantly, through on-the-ground partnerships with community organizations and residents of the built environment that has helped us develop a framework for a participatory software design process. So at the lab, we pursue these goals through four main research areas. We develop visual tools for geospatial computing, tools for design collaboration, participatory models that can help us with civic data production and community-based technologies or civic technologies. All of this work, like I mentioned, is importantly grounded on critical inquiries into the history of spatial technologies, which is also the main theme of my upcoming book, due in a year and a half. So drawing out the computer map, the title of the book, is an attempt to surface the historical connections between design practices, extractive economies, different corporate interests, to look into how tools for computer mapping in the second half of the 20th century were built initially to support designers and planners, then eventually led to the development of a multi-billion-dollar geospatial computing industry that ironically is now incompatible with design tools and approaches. So one of the interesting things about the history of computer mapping is that in 1963, Howard Fisher, who was actually an architect by training and did not have a background in computer science or geography, created CMAP. CMAP was a fundamental and foundational computer mapping software in the second half of the 20th century. And he created CMAP by engaging his design background and his design thinking. Fisher was more interested in improving the aesthetics of computer mapping. He was not interested, as many of his contemporaries, in optimizing how maps were produced, making maps quicker, or mapping with more accuracy. He was mostly interested in devising a way to represent spatial information in a way that was ambiguous and accessible to planners and designers. So he actually, because computer screens were not broadly available at the time, what he ended up having to do was figure out a way to hack line printers to overprint characters in the same position to create shades of gray that could be printed out on maps. So as you can see in these drawings, Fisher's maps were much more accessible and easier to interpret than other approaches to computer mapping in the 1960s. This was a more intuitive graphic medium that allowed architects to use computer mapping in their day-to-day practice. Apart from the graphic representations and intuitive maps, CMAP contributed to computer graphics with an algorithmic innovation, which was spatial interpolation, which again, Fisher created to give designers a more intuitive and graphic way to communicate the relationships between people and the built environment. The graphically intuitive maps that CMAP created allowed architects, landscape architects, planners, and policymakers to come together in the same space to design together the built environment. But later, as Fisher and others directly engaged CMAP in their design and day-to-day practice, they also realized that the algorithms that were behind the graphic representation of CMAP could also be used to improve the analytic capacities of spatial mapping software. And more importantly, because information was now represented symbolically in the backend, it was easy to engage computer mapping programs with rational modeling approaches of the second half of the 20th century, like operations research and system analysis. So this idea of marrying computer display of information with spatial analysis and operations research instantiated a very particular view of mapping as a tool for information management and rational design. And when smaller computers became broadly available in the 1980s, Jack Dangermond, who was a student of Fisher and the director and owner of Esri, the monopoly that runs the GIS industry nowadays, he realized that computer mapping programs could be very profitable beyond architecture and planning, which ultimately does not have as much money as other industries like oil and gas. So Dangermond and his team sought to formalize the practices, computer mapping practices that were embedded in CMAP and some of these early computer mapping programs into a generalizable software system. So the system that Dangermon and Esri devised had a fundamental data structure that consisted of points, lines, and polygons with attributes, which essentially allowed Esri to represent anything in the world through the same information model. And then it also allowed them to turn drawings into a spatially enabled database. So anything in the world had to be represented in this reductive and general manner. This model of representing spatial information is still very much ingrained in modern GIS software. It defines how spatial information is represented computationally, what gets counted, who gets counted, and how designers and community members can engage with such tools. So my upcoming book, I don't think of it as just an attempt to historicize the past. I believe that the history of computer mapping can also show us the future potentials of computational design and mapping tools. Painting with Data is an open source mapping software and visualization platform that I developed several years ago while I was in grad school. And this was an early example of how these lessons of historical research could be directly extrapolated into new tools for design and planning practice. So this work incorporated the original focus of CMAP by allowing designers to compute with information visually and intuitively, supported by the system's real-time visual outputs and interactions. Painting with Data represented spatial information through voxels, geospatial voxels, which merged the graphic representation of information with its backend computational representation. With voxels, multiple layers of information were visualized concurrently, allowing users to make visual correlations instantly and on the fly. For example, users in this case can immediately see the correlation between a high incidence of asthma and lower home values in New York City. Through a visually driven approach to spatial analysis and mapping, Painting with Data reduced the steep learning curve required for most existing GIS software. Painting with Data enabled users to rapidly create spatial models on the fly based on the real-time visual feedback that was provided by the interface. They were able to combine this feedback with their subjective information, understanding of information. Additionally, for those that were interested in building spatial models beyond the visualizations, it introduces a visual programming interface that through drag and drop building blocks allowed users to develop real-time geospatial models, extending the mapping and analytical capacities of Painting with Data. This work was successfully introduced in academic settings and through partnerships with nonprofits and community organizations in Massachusetts, where I live. And it expanded to eventually reach 3,000 users per month, which included designers, students, and educators. So the next project that I'm going to share is called Drawing Participation. It expands on these early lessons and the capacity, spatial analysis, and graphic representation capabilities of Painting with Data, and then adds a layer of planning and design collaboration on top of it. It enables users to sketch, draw, design, and deliberate collectively, all within a geospatial platform. As I have tried to argue throughout this presentation, I believe that improving public participation within the design of the built environment is essential. This is especially true in contentious design scenarios that involve multiple stakeholders. But I also believe that one of the biggest challenges to enable community participation in the design process is the largely political and social complexity that participation requires. Public participation as it stands currently is largely done in person through an analog methodology, which is profoundly disconnected from the digital methods that are actually shaping design decisions at the end of the day. Additionally, existing participatory methods in urban planning and urban design have been shown to have a number of limitations, which include barriers of entry, not allowing everyone to participate, issues of equity. They are too narrowly focused on specific methods, and obviously they have scale limitations. You cannot run in-person workshops to include everyone. So with drawing participation, we provide a framework that incorporates principles of both collaborative planning, the idea of enabling large-scale deliberation, groups to deliberate together, and of participatory planning to support large-scale community engagement processes. So with this work, we provide a customizable digital framework that allows designers and planners to support large-scale participatory planning and design processes without the need of a technical background. So we provided building blocks that planners can then put together into custom participatory platforms for their own purposes. All of this in a contemporary, easily accessible, open source, web-based platform. Our framework integrates drawing, data collection, simulation, and spatial analysis, bridging CAD, GIS, and community participation in a single visually based platform, all while allowing multiple users to work together in real time. And on top of this, we built a spatially enabled version control system that allows either single users to browse in time across their proposals, or multiple users to browse through discussions through each other's proposals and ultimately deliberate to come up with a common ground representation. Our component-based architecture allows community organizations, whether municipalities, federal governments, or NGOs, to easily implement and scale modules that include surveys, civic data collection methods, co-design proposals, participatory spatial analysis methods, and community deliberation, again, without the need of technical background. So they can mix and match all of these components to build their own interfaces on the fly. Our toolkit was developed through a community engaged process through which we came up with 5 principles as we build this software. First principle is providing users with scalability and flexibility. Again, mixing and matching different ways of participating, context specificity, which is relevant in geospatial platforms, to allow users to work with a projection and a spatial projection that makes sense to them, and to allow them to customize their interface according to their needs. Collective goal setting, which similarly to how software developers build software together, residents can take different proposals and build on each other's ideas in a structured manner. Design synthesis. Through machine learning models, we are able to blend between geometrically distinct proposals to find a middle ground intervention. And low-tech, high-tech, which allows users to both engage with digital and physical representations of information according to their needs. So one of the initial partnerships that shaped this framework was with an NGO based out of Ukraine. We work with the city of Vinnytsia and local planners. Vinnytsia is a city of around 400,000 people in central Ukraine, where 64 small rivers end up coming into the city and facing environmental challenges such as pollution and gray zones with vulnerable populations living around the area. So the municipality has come up with a proposal or a framework for development around the rivers called the Small Rivers Project, which aims to create continuous green corridors for both people and wildlife and to improve the overall river ecosystem. However, their in-person workshops and community engaged processes have been severely limited during the war with Russia. And digital tools have actually emerged as a solution to engage with residents at the scale that they need and want to. So local planners leverage our interface and our framework to develop a visually based spatial survey for residents to share their perceptions for public space, safety, accessibility, and some of the environmental concerns that they might have around the rivers. They called it Hurtoma, which in Ukrainian means together in a big group. So with the toolkit, planners were able to set up an onboarding process that includes some simple registration to know what demographics of people are participating in the exercise. they were able to use the different map styles and spatial projections to then come up with a step-by-step guide that surveys residents on different feelings and thoughts that they had of the built environment. This lets them map and add different spatial features on the fly. Participants and users can add points, geofences, upload photos, leave comments, and even audio or video to share how they feel about the built environment. At the end of the survey, they get a screen or a map that shows everyone else's participation and the positive and negative experiences that residents have around the rivers. They can also use the components that we have, spatial analysis components that we have built to do some very basic spatial analysis that can help them interpret and inquire into the results. Ultimately, the interfaces that we have built have allowed planners to essentially take the results and the feedback of the residents and incorporate the surveys directly into their design process. In terms of engagement and impact, in just a couple of months of operation, the platform recorded over 3,000 contributions from over 600 unique users, which is much more significant than the in-person workshops that they were running. According to our partners, Hurtoma proved to be a much more cost-effective and time-effective application compared to other exercises that they ran in person in the past. They believe that the platform captured more nuanced insights and facilitated deeper analysis and deliberation compared to other methods. Residents also highlighted that they felt cared for and that there was a feeling of transparency that was provided by the exercise. So in a different case study, we have been leveraging the same framework in partnership with the Mansueto Institute for Urban Innovation at the University of Chicago to engage with the complex issue of designing with different informal neighborhoods around the world, but mostly in Africa initially. Currently, about 1 billion people around the world live in the so-called slums, and most of these spaces lack land tenure, physical access to their residences, and which ends up resulting in not having basic human services like water or sanitation. The process of providing basic human services to these neighborhoods or of redesigning their spaces is even more challenging and is usually divorced from any community impact. It happens in a top-down manner. So as you may know, researchers have leveraged AI and satellite imagery to produce large-scale data sets that have given us building footprints across the world with different results in different regions of the world. So as part of this process, our colleagues at the University of Chicago created a framework that have leveraged the building footprints that are openly accessible to characterize millions of underserved communities and to describe some of the spatial issues that they face. For example, this neighborhood does not have direct access to the streets surrounding the neighborhood for the most part, and this also impedes the provision of basic human services. So where water pipes would usually go under the streets, because the houses are not directly connected to the streets, it's really hard to provide water and sanitation services. So in an early version of this work, done in collaboration with Luis Betancourt at Chicago and Nicolas Demoncho at MIT, we tackled the challenge of providing human services like roads and sanitation to all the houses in some of these neighborhoods, initially through a constraint optimization algorithm that generated in a stepwise manner a new street network to connect each of the houses to an existing road with what we thought was minimal disruption and cost. This algorithm was then visualized in a web interface. But as we found out, each of these neighborhoods, it's much more complex on the ground, and it cannot be understood solely through maps and computational models. Residents simply could not agree to any of the proposals that were generated by our constraint optimization algorithm. In this case, our algorithm suggested to demolish different streets on a stepwise manner, and obviously nobody wanted their house to be demolished. So what we thought was an optimal approach, at least computationally, because it minimized cost and disruption. In fact, it was suboptimal on the ground. And this is because there are so many stakeholders and personal interests that are part of the reblocking or redesign process. So we argue that community participation is required to successfully incorporate the different individual interests and different local impacts that residents face in these neighborhoods. So what we're doing is leverage drawing participation to enable local residents across the world to be a part of this production of local cadastres in a scalable manner. So we built an extension for our software, which includes first a generative ensemble AI model that allows us to produce a baseline plausible parcel map based on satellite imagery of existing building structures. Secondly, a drawing participation interface that enables residents of informal neighborhoods to modify the baseline parcel maps that our models produce in a crowdsourced manner. And finally, a version control system that can record and synthesize all of these competing resident proposals to eventually arrive to a common ground neighborhood parcel map. So our model is trained with global parcel and building maps, and we are able to predict a plausible parcel map based on existing building footprints, which are openly accessible globally. So once we train our models, we can then pass building footprints, and our models will provide us with a plausible parcel map that then residents can modify through our interface. So all of our models are open source and available on GitHub. And when users use our models, they can develop their own vector datasets of other regions of the world that we're not currently focusing on. So again, once these baseline cadastral maps are developed, local residents can leverage our software to correct and deliberate on the ground on which parcel representations are more accurate. So through on-the-ground exercises, we've been able to engage with a large group of residents, designers, and policymakers to collectively develop design proposals that ultimately satisfy different competing interests. And this process, we believe, can be replicated potentially across many different informal communities across the world. Obviously, we've run into different issues and different opinions of what different parcel maps are. And we believe that this process is highly contextual. So we developed a version control system for spatial information that allows all of these proposals from different residents to be recorded and viewed concurrently to identify potential conflicts or synergies among them. As part of this computationally supported process for deliberation, we also develop models that allows designers and community members to synthesize among potentially thousands of proposals, so you can merge and blend and interpolate between different proposals while preserving the topological connectivity of the network. So because we have been grounding our work and our development process in real world problems, we believe that we have been able to push computing beyond existing interfaces to develop, for example, information models that allow many users to work concurrently, a set of algebras and machine learning approaches that help us synthesize through large sets of user proposals, user interfaces that are accessible to non-technical audiences, and version control systems that can support spatial information. This work is actually now being extended in partnership with the federal government of Mexico to develop the first community-engaged nationwide cadastral map. In other work at the lab, we're exploring first the ways in which AI models can support the production of civically engaged information. And we're also looking at how user participation can support the development of more contextual and nuanced AI models. This area of research cuts across some of our different projects, just like the building to parcel model that I just shared. And in a different ongoing project, we're actually building an open and consistent urban building modeling database that integrates computer vision, participatory AI models, and state-of-the-art building science approaches to provide an urban building dataset and environmental performance evaluation method that can enable sustainable and resilient development in data-poor contexts, just like Africa. So as part of this work, we're leveraging openly available building footprint datasets, street view imagery, and computer vision to provide a rich multi-dimensional model of 5 cities in Africa. So through a combination of image segmentation, edge detection, vanishing point estimation, and crowdsourcing, we are able to produce detailed multi-dimensional models that include building geometries, embodied carbon, material data banks, and building typologies, which will ultimately enable building scientists to integrate environmental data with geometric and non-geometric information of buildings in the cities in Africa that we're working with. They'll use this database to produce a detailed analysis of the environmental performance of buildings, and this will also enable them to provide design recommendations for healthy indoor environments in a changing cities in Africa. So the last project that I'm going to discuss today had the goal of developing design technologies to expand the social and ecological impact that urban farms and community spaces can have across New York City. Drawing together, also the title of this presentation, is a partnership between Green City Force, or GCF, and researchers at MIT and Northeastern. Our partner, Green City Force, is an AmeriCorps program that trains young adults living in New York City public housing, or NYCHA, which is composed of almost 300 developments that house a combined population of over 400,000 people, which is huge. That's the size of an American city, for example. NYCHA residents are challenged by systemic barriers to economic mobility, such as low employment and educational attainment rate. GCF has developed a network of 6 community spaces, or eco-hubs, across different NYCHA developments across the 5 boroughs of New York City, which have turned underutilized areas in the developments into working farms that combine workforce development training and community programming. Our partnership began with the vision of developing new design technologies that could help GCF design twice as many eco-hubs in the next few years. But as we engaged with the staff and AmeriCorps members, we realized that the secret sauce of GCF was the strength of their community connections. Through personal engagement, for example, through farm stands or door-to-door canvassing, they were able to drive positive change in their neighborhoods. So instead, we worked closely with GCF to map out their existing practices and data pipelines, which at the moment mostly consist of analog surveys or Google spreadsheets that are all over the place. And we instead focused on creating a modular and reusable set of technologies, which organizes the many sources of information that they have into a central model that can provide insights that they can use for their day-to-day operation. This is very important, and it helps them support the recruitment and retention of the AmeriCorps members. It helps them measure the social outcomes of the program to access in the future diverse mechanisms to support their work and newer eco-hubs, and also helps them inform the design of the future eco-hubs. A core component of this process has been the development of digital platforms to support the recruitment and engagement practices that they have in ways that better align with young adults that live in public housing in New York City. This includes storytelling and visual media through interactive platforms, and it will help them, or it has helped them scale up the recruitment of new AmeriCorps members, while providing new engagement metrics, which translate into reaching a larger population. As part of this set of modular and generalizable urban technologies, we also are developing or have developed a sensor toolkit that is open source and allows them to measure the hyperlocal environmental conditions of the eco-hubs. This sensor toolkit essentially has the capacities of a weather station, but but it costs a small fraction of what a weather station would. And more importantly, it's buildable and serviceable by AmeriCorps members because it's made out of off-the-shelf components. These units help us visualize the environmental offsets that GCF's eco-hubs have had across NYCHA developments. As part of the system, we built an online hub to gather different government datasets and citizen science initiatives and datasets into a single centralized representation. And we have created indices that inform us about the community health of the spaces and combine traditional datasets with real-time environmental information. All of these interfaces have ever since been expanded to other areas such as Boston, Monterrey, Mexico, and Oakland, California, to support urban farm impact assessment, users advocating for air quality and different environmental policies, and for environmental education. The application that we developed in the front end can be customized by users through a graphic framework, which allows them to deploy new environmental monitoring applications based on their specific needs and requirements. So they can essentially take the software that we built and create new applications for their own purposes. The data products and visualizations that are created through our applications have been used by community advocates to create printed media and to communicate with residents in a more inclusive manner. Things like what impact are the farms having in their environments. This work is currently exhibited as part of the Venice Architectural Biennale. And lastly, in the next couple of years, GCF has the goal of doubling the number of eco-hubs or farms that they have across NYCHA. However, at the moment, they have a very analog and in-person way of surveying different possible locations, which makes this goal unfeasible. So in collaboration with GCF staff and AmeriCorps members, we developed a site allocation mathematical model that can help them increase the impact of the new eco-hubs both locally and globally while balancing benefits and trade-offs among different decisions. The site allocation model allows GCF to interactively define different contextual constraints in their site selection process and to receive real-time feedback of their decisions and trade-offs of those decisions as well. With their feedback, we have built graphic interfaces that translate between the model and GCF staff decisions and ways of thinking. Through the software, users can interactively specify the best demographics for new AmeriCorps recruitment, balance the accessibility of the spaces throughout the city, focus on sites that are at risk of flooding, specify how much space they need for a new farm, and they can also choose to prioritize existing bills or political support systems that can enable the new eco-hubs to exist. They receive real-time feedback of the trade-offs, relationships, and spillover effects across scales and geographies. This is the underlying mathematical program that drives the decisions being displayed in the software. I believe that this work is an example of how, through close engagement with real-world design problems and communities, and through collaborations across disciplines, we are able to advance computing and computational design towards a social good. So to circle back to the beginning of the talk, I believe that the biggest potential of computing in the design of the built environment is not so much to bring back mid-20th century goals to optimize how we design spaces. But instead, I believe that computing gives us the opportunity to bring together architects, landscape architects, planners, stakeholders, and the communities that they serve together in the same space to work towards assigning shared and equitable outcomes for the built environment. So as we think about the future of the architecture of our software and the architecture of our cities, I always like to remind myself of CMAP, which was short for scenographic mapping, a neologism for drawing together. Because it is here that I believe that computing can have its biggest impact as an instrument to connect multiple communities and disciplines in the design of the built environment. So thanks so much for hanging out today. And yeah, looking forward to your questions.
Thank you, Carlos. That was a quite interesting talk. Um, are there any questions online? You could just speak up or raise your hand. I guess as people think about it, I do have. Oh, Kian, why don't you go ahead?
Okay. All right. Thank you. Good to see you again, Carlos. Thank you so much for coming to speak to us today. Really appreciated the talk.
Good to
Um,
speak to you.
I'm, we're really very interested by the topic of sort of participatory design, or, obviously it's a big theme for you. How do we engage people more in the design process? I just kind of like to hear you talk more about the opportunities and the risks associated with AI when it comes to participation. Because, of course, it could be a great way to bring people in, but it could also be a good way for us as designers to make assumptions about people, right? So, what are your thoughts on that front?
Yeah, thanks for the question. It's complicated. Yeah, I mean, obviously, a lot of the work that we have done has focused on first trying to use AI to sift through large amounts of information and to help us scale up the production of information. But then simultaneously, it's a challenge because we need to validate the information and the data that we're producing with AI systems, and validate the interactions that we have between users and our systems. So I think, I mean, obviously, as we have implemented these tools in practice, one thing that we have found out is that the models undercompensate or underperform in communities that are less representative in existing data sets. So, for example, when we try to predict how parcels will look like in Africa based on data sets that have been built through West West American cities, it messes up really badly. So that's where I believe that involving direct participation of users can help us sort of correct or have a more nuanced understanding of what the space might look like. So one of the challenges that we have had is balancing both the use of the models and the production of the models. But one of the things that the work of the lab has done for us is that by engaging participation and large scale participation through computational design tools, we can start to scale up the production of these models. Like a couple of years ago, it was mostly me and some of my students sitting at our computers and manually encoding or correcting the models. But nowadays, with our tools, we can engage larger residents of the actual communities to help us with the process in a more contextual and nuanced manner. So I believe that it's both a risk and an opportunity. So as long as we engage the people that are going to be affected by the models, we can steer towards the right direction.
Great. Thank you so much.
I have a question. I know that a lot of your work is focused on not just bringing the data together, but also reaching out to the community before a project is implemented. What kind of process do you have for like measuring or surveying the participants or the stakeholders after a project has been implemented to make sure that the goals you're aiming for actually landed?
Yeah, no, that's a great question, and it's complicated. I think ultimately one of the things that we have realized is that this process takes a lot of time, and one of the challenges that I face as an academic is that first of all, the academic calendar and the academic timeline rarely matches up with the complexity of public participation. So I think the first thing is to acknowledge that it's a complicated and lengthy process, but ultimately it can result or have outcomes that are more long lasting and more impactful. So as you mentioned, the first step in engaging with a new partnership is having those conversations before we start out with any process. And one of the biggest lessons in that regard was with the project with Green City Force, which Prue might be a little bit familiar with. But we started out with the idea of like, we're gonna come in, we're gonna build software that can help you double the number of urban farms that exist in NYCHA developments. But through difficult conversations with staff and the director of the organization, we realized that even though that's what they at first thought they wanted to do, what they were hoping and wanting to do was a little bit different. So we had to completely reframe our plan and the things that we were aiming for to help them kind of like scaffold a system of urban technologies to support the operations of the program to eventually get to where they wanted to be. So obviously that has pushed the timeline back to some of the initial goals that we had. But we also believe that it has resulted in a long-lasting partnership, and we believe that the residents of NYCHA are more appreciative of this smaller interventions that have helped them on their day-to-day lives. So I guess to circle back to your question, it's a complicated process which involves listening closely and giving away a little bit of the authorship of the process and let people make decisions and just the role of the software designer or the architect is a little bit less directive and more listening and mediating conversations rather.
Awesome, thank you. Are there any other questions from the group? Well, if not, I guess then let me take this opportunity to thank Carlos again for graciously spending time with us and for his wonderful presentation, very insightful, really incredible projects. So thank you for being here. And yeah, I don't know if you have any final words.
Yeah, no, it's fun. Thanks for your questions.
Great. Well, with that, I guess, G, I can hand it back to you, or
Yeah, so I will share the recording for folks who couldn't join today. Sorry I had to have my camera turned off due to my unstable Wi-Fi, but thank you, Carlos, for joining, and thank you everyone for your time.
Thanks, everyone.
Thanks, Carlos.
Thanks,
Good one.
Carlos.
Thank you.
Bye.
Bye.